So what we have here is our equation that shows the second law of thermodynamics, and it's also our criteria for whether something will be spontaneous. And if you recall, we said a spontaneous reaction requires that delta S net is greater than 0. So another way of saying that is for any reaction to be spontaneous, the net entropy of the universe has to increase. And we broke that into two parts where we said the entropy is the entropy of the surroundings and the change in entropy of the system. And we were able to redefine this term of entropy of the surroundings in terms of the system, in terms of the heat, the enthalpy. And so we can rewrite this equation to say that our delta S net is equal to negative delta H of the system over T plus delta S of the system. And so this was the equation we were using to determine our spontaneity of a process. There's a couple problems with this equation, and one of which is it's really hard to determine what this term is. What is this change in entropy of the universe? That's a very difficult thing to determine. And so what chemists have done is they've taken this equation and we've defined a new term. And so I'm going to show you how algebraically we got there. And so I'm going to start off and I'm going to multiply everything by negative t. Okay, so we're going to multiply everything by t, negative t, and so we get negative t delta S net equals delta H, because we've removed that negative and then divided by t, and now minus t times delta S of the system. So now we have a term where we have this negative t delta S net is equal to delta H, and that's delta H of the system minus t times delta S of the system. What chemists then did was they defined a new term. So we're going to define a new term. And they're going to say that this negative t delta S net is defined to be delta G. And delta G is what we call Gibbs Free Energy. Okay, and when we look at that and we see this delta G term, right, we now have an equation where delta G is equal to delta H minus T delta S. And in this equation, everything refers to the system. So I dropped the subscript cis from these because now we have an equation that says everything is of the system. And this equation, delta G equals delta H minus T delta S, is probably the single most equation that you will see in general chemistry. This is our criteria of spontaneity. And I want to look at this and just recall, we said a reaction is spontaneous when delta S net is greater than 0. But if you think about our equation down here for delta G, right, if delta S net is greater than 0, we're going to multiply that by negative T. And so our reaction is spontaneous when delta G is less than 0, right? And that's because we have this negative sign here. So if delta G is less than 0, that means that delta delta S net is greater than 0. And when we think about this equation, the other nice thing of what it does is it's a new thermodynamic variable that's put in terms of our delta H and delta S. And so we can think about this, we can think about our various terms. And so I'm going to write a little table here. We have our delta H, delta S, and delta G. And so we can build our table. Those are our terms. And up top we'll say when these terms are negative or when these terms are positive. What does that mean? Okay, and when we think about that, if we think about delta H, if delta H is negative, that means it's an exothermic reaction. And that's a favorable process. We're going to use the word favorable. When it's a positive delta H, that's an endothermic reaction, and that's unfavorable. Now, in terms of our change in entropy of the system, we said when delta S is negative, that's an unfavorable. We're losing arrangements. So when delta S is negative, that's unfavorable. And when delta S is positive, that's favorable. Okay. When it comes to delta G, we're going to say when delta G is negative, that is our spontaneous reaction. And when delta G is positive, that's our non-spontaneous. And so when we go back to our equation, delta G equals delta H minus T delta S, we can see we have two terms, both of which can help make delta G negative and spontaneous. So if delta H is a huge negative number, a very exothermic reaction, that's going to help make delta G negative and spontaneous. By contrast, if delta S is a huge positive number, right, then this term, since we're subtracting the positive number, will make delta G negative, and that'll be favorable. And so when we think about what makes a process spontaneous, what makes it favorable, it can either be driven by delta H being very exothermic, or delta S being very positive, making this overall negative. In some cases, both are true. We might have an exothermic reaction that also has a huge increase in entropy, and that's a reaction that would be a very spontaneous event. Now, when we think about the Gibbs free energy, so Gibbs free energy, right? So that's our delta G. So what do we mean by this free energy? What that really means is the free energy is really the energy available to do work. So sometimes you'll see this, the Gibbs free energy is equal to this maximum amount of work. This is the energy available to do stuff. So when we calculate a delta G, that negative delta G, that's spontaneous, that negative number that we get, that's the energy we can harness to do something. If it's in our body, it might build a protein, move a muscle. If it's in a car, that's the energy that we can transform into movement. That negative delta G is the energy that is available to do stuff. And that's where the power of this Gibbs free energy is. This calculation of delta G, this negative delta G, when we have it, that's the energy available to us to utilize in some fashion. All right, and now we have a way of calculating it with our equation. We can see delta G, and a lot of times you'll see this under standard conditions, is equal to delta H minus T delta S. So we already know ways to calculate delta H, and we know ways to calculate delta S. And so now we have a way to calculate delta G through that for any given temperature.